So last week in EEG we saw some basics about data acquisition and that was and artifacts. So we discussed data acquisition, how the setup looks like, and what kind of artifacts you can get. Most important, of course, the eye movement artifacts. And then the next section is now on artifact correction and averaging. Averaging meaning computing event-related potentials. And there's actually not that much to discuss about this. The main thing is on artifact correction. So before going into a little bit of details, it doesn't hurt to talk about some concepts of artifact correction to give you kind of a framework that applies whenever you do some artifact correction to any kind of data. So that's the concept of artifact correction. Then we talk about something that's quite popular in EEG for some reason, which is ICA-based artifact correction. We will not do that in too much detail, so this will be kind of the cognitive neuroscience / psychology ICA story. Really, ICA is a interesting latent probabilistic modeling technique, but we will not go deep into that. Then some event-related averaging, and finally some ERP quantification. But especially for these two last points, I have, sometimes I have my own opinion about them. So let's see what's happening. So what is, I think, really important and also quite intuitive is that if you're talking about artifact correction in any kind of data processing, it makes sense to classify the procedures that you do into certain substeps. And the first substep is usually artifact detection. So if you want to somehow make data cleaner in the sense that you don't have artifacts in there, you of course first need to have some means of detecting an artifact. And this is, of course, in software solutions usually done by means of an algorithm that somehow figures out when there was an artifact. For example, if you have epoch EEG data, so basically, you know what epoch EEG data is by now, I hope. Then you can classify each epoch as either being artifactual or artifact-free. And you can do that by hand. And if you have very few EEG epochs, it actually makes sense to also check the results of algorithm by hand. If you have really many, then there's a trade-off between how many you can look at and where you trust your algorithm to do that. Then, once you have detected artifacts and, for example, classified EEG epochs as either artifactual or artifact-free, you can do two things. You can either reject artifacts, so that means that in this case you would just not process a certain EEG epoch any further. And then if you have an artifact on a single or a couple of electrodes, like we've seen last week, where you have the eye movements maybe only on the frontal channels, you might want to exclude all channels because there was an artifact on a certain epoch. You might not want to do that if your data is very valuable, but in principle, the standard procedure in EEG would be if you have an artifact, like an eye movement in a certain epoch, you would discard the data from all channels, also, for example, the occipital ones where you actually don't see the artifact. Another option that you have next to artifact rejection is actually artifact correction. And there what you're trying to do is subtract the artifactual activity from EEG data and then have kind of a clean EEG data afterwards where you don't want to exclude data but modify it. And this is of course a step where you change your raw data to something artificial, which you then say, okay, this is now the data that I want to work on. So these are three things that you can do. So to do something with artifacts, of course, you have to detect them. And then you can essentially decide, do I want to reject them or do I want to use some correction? And there is no wrong or right answer, whether you should reject or correct. They basically follow the mainstream because because there's this social incentive or social pressure system that if you do something fairly idiosyncratic, people that review your work will say, that's fairly idiosyncratic. Why isn't he not or she not doing what everybody else does? Good. Then there are some general points about artifact rejection and correction that you always should keep in mind when you're applying artifact rejection or correction aspects. So this is related to all of them essentially. So first of all, detecting artifacts is a threshold-dependent signal detection problem, which means that you will have misses and you might also have false alarms. That applies whether you do it by hand, by looking at the data, or whether you use an algorithm. Yeah, so you will always have that. If you use a more stringent criterion, then you will have more false alarms. If you have less stringent criterion, then you will have, of course, more misses. So you always have these kind of signal detection trade-offs in artifact rejection and correction. Not all artifacts are equal in the sense that if you, for example, eye blinks, if you assume that a participant in the EG experiment that is who is presented over time with different conditions randomly, that means uniformly, blinks, and there's no association between your condition of interest, for example, looking at faces, and your condition of no interest, looking at non-face stimuli, then it's not necessarily problematic, because what you will have as a difference between your condition should not be driven by the artifact. Yeah? So the real problem is if you have a certain condition where people are, for example, prone to blink a lot, and another condition where they are not. So for example, if you do these puff experiments and then your condition is puff versus no puff, then it's maybe not the nicest EEG experiment. Always important to know is that, of course, your artifact rejection and correction change the data set. And this is something, so you always need to keep in mind whenever you're pre-processing data or do some kind of artifact correction that you change the data. And then if you do the pre-processing or the artifact rejection, which is part of pre-processing, of course, differently, you will have changed the data differently. Yeah. So this is just something you need to appreciate, and then from my perspective also not to get too worried about the wrong or the right way to pre-process data. The wrong or the right way to pre-process data or do artifact correction is determined by your peers. Your peers will tell you, nah, that's not how one does that. And if you feel that the majority of peers says that, then you can either think the majority of peers has no idea, but I need to pay my rent, so I do what they say. Or you try to convince them that you're actually on the right track. So you can decide that. So, but there is no wrong or right way. There's just a social agreement that certain ways, for example, the COBIDAS report is a good example. That's kind of an agreement by some people who the community more or less thought they should represent the community, what they think, but it's not that they are right and somebody who thinks it differently is wrong. So that's important. Maybe more important even than this, that you know that there's no right or wrong way, is that that it's good practice to know how artifact rejection and correction affects the results. So especially for ERP stuff, I really recommend to do the analysis with different pre-processing steps using different artifact correction methods, and then look at the results, and then basically know what the difference is and whether you can feel like you can ignore these differences or you should be worried in the sense that they actually affect your conclusions. And I also agree that visual inspection of single epochs can be helpful, so that should be done. And then an important thing in EEG artifact correction is that last time we talked about artifacts like muscle stuff and so muscle artifacts or rolling eye movements or alpha. Essentially, you try to avoid the muscle artifacts and alpha by telling your participant to concentrate and not grind their teeth. And then what is actually left in the data are eye blinks. And this is where people actually use artifact correction. And this is now then the first thing about epoch data, where a way to detect artifacts, in this case blinks. So here you should have, what you see is an epoch of a given electrode. Forgot. Here you see an epoch of a certain electrode, so you see a potential trace, and you see that at one point this potential trace exceeds a given threshold, here minus 75 microvolt, and sometime after stimulus onset. And when we looked last week at blinks, this is something you would see if you look at all the EEG traces, but of course you see it also in one electrode. So then the question is, how do I now detect these blinks? And one thing is to use an absolute potential threshold, in the sense that I classify an epoch as an artifact if one sample of this EEG trace of this electrode exceeds a potential of plus or minus 75 microvolt. And then for this kind of epoch, this will make a lot of sense, because at baseline it's roughly around 0, and then you exceed that. Now, if you in your pre-processing have things like that, you have a deviation from 0 already at baseline, then an absolute threshold might not actually detect such a blink, because you have this baseline shift, and then actually the blink is within your threshold bound, and you will not detect it. So that would be a miss. On the other hand, you can of course also have a false positive, in the sense that you have the same baseline problem essentially, because, for example, you didn't baseline correct. Then the data of a single electrode exceeds your threshold, although that was not a blink. So that says essentially that absolute threshold-based artifact correction, especially if you don't do a baseline correction, or as shown here, a drift correction, so basically using a high-pass filter, if you don't account for drift that might be in the EEG trace, then you might miss out on blinks. So in general, one can then say that peak-to-peak thresholds are preferred. This means that instead of looking at the absolute threshold, you compute for each, over a given time window, you compute the difference between two peaks, and then if there's a change, so you're essentially looking for a change. If there's a change that exceeds, not necessarily but so you either can define two peaks that are somehow adjacent, or if you find very fast changes between two adjacent samples that are quite big, then you call this an artifact. That being said, of course, you can also use absolute threshold artifacts, especially if you have done a baseline correction and or high-pass filter, so accounted for drifts. Then, of course, the thresholds, absolute potential thresholds, also get stuff out. So, yeah, questions about? Well, that would be an empirical question, and would be an empirical research project. So I can't say. Oh yeah, from my experience, I had these experiments with really many trials, so like 20,000 trials. So then I trusted the threshold and made those quite small. So and then I haven't checked all the 20,000 trials where this might have happened. So I think I wouldn't think that it happens so much actually, but it's still something to think about, and it motivates, of course, why you, for example, in SPM have multiple options to do artifact correction, not only with an absolute threshold, but also with a peak-to-peak or with a change threshold. But they then have other things that one needs to look out for. So the easiest is that you have a kind of a simple experiment where you still can look at the EEG traces. For example, in the old PhD data set that you're looking at, There we could have actually done that, but I didn't do the eye movement pre-processing there because Camilo Pucao, who was the postdoc there, he had this awesome ICA-based thing, at least that's what Andy and he thought. And so they did some artifact correction on that, so I don't have first-hand experience of how many blinks you get there. I wouldn't think it happens that much. If I'm prone to give an estimate, I would say 5%. Other questions? Why it happens? Why? Drifts you can have sometimes in EG. I mean, it's unlikely that you actually have this drift on a single on a trial, but you can have overall drifts if the relation between, especially if the reference electrode changes. So if you have the reference electrode and everything is with respect to your reference electrode, and then maybe the reference gets a little bit loose, or it gets actually a little more, gets better connection, then you sometimes have these overall drifts in the signal. So this is from the book. So this is kind of a book idea that this can happen. I don't think this happens a lot, but it's more like that one should also think about threshold corrections and what they really mean on the epoch level. And if you have experiments where you can do this, so if you have like, I don't know, if you have two conditions and you have 200 trials per condition and there's some sense in looking at them, then you might detect more blinks. But of course you also, if you're doing visual epoch classification, you're not only looking at single electrodes, right? You look at all 64 channels and you more like try to monitor overall 64 channels. This is not marked as a back trial by my algorithm. What do I think? So that was already the introduction to concepts of artifact correction and a very, so one could go on for ages about these eye movement artifact correction algorithms because they're all different versions and so on, but I try to actually keep that short. This is still from the time when it was actually much more mandatory to do these kind of SPM analysis. What we did then, and I think I will have some stuff of that later, was to actually compare different pre-processing techniques and get a feeling how different artifact correction techniques affect that. So one could go more into details, but it's not worth actually discussing them under a no practical perspective. So the next thing that then is quite common for eye blink correction beyond these simple threshold detection or peak-to-peak detection things is ICA-based artifact correction. And personally, I don't know why people love it so much. It seems to be fascinating also for people that enter EEG. So, for example, Stefan Appelhof, who's now a PhD student, he also loves this ICA-based artifact correction, or at least he spent some time, or quite a lot of time actually, on ICA-based artifact correction. I don't know. I find it like it's a model, but it's not a biologically motivated model. So I think it's like, whatever. I think the motivation why some people love it is because it's model-free, which is not the case. It's not model-free. But it does something automatically and you get the feeling, okay, I just let the data speak for itself until a certain point where I then decide, but this is what people then are okay with. I don't know. ICA-based artifact correction. So I'm giving you the cognitive neuroimaging EG story about ICA, not the formal story. So what is the intuitive story? The intuitive story is that on electrodes, you observe these kind of fluctuation, right? So you have on a given trial, you have an electrode 1, you have an electrode 2, and you have an electrode 3, and you see the gray line, which is the voltage fluctuation on, let's say, a single trial. Now, the idea of ICA is that what you see on the electrode level is actually a linear weighted combination of some latent components which are independent in a specific sense, which we'll get to. And so there are these latent, what I called components or independent components that you don't directly observe and which need to put together by a set of weights. So here you have weight 1, 1, weight 1, 2, and weight 1, 3, which determines how much of the trace or the variation here in C1 enters into the mix for E1, E2, and E3. And as you can see, if you look at that not from the perspective of the component, where you then have weights here, but if you look at it from the perspective of the electrode, then you see that each electrode time trace gets contributions from all the 3 components by means of these weights, W11, W21, W31. If you're familiar with artificial neural networks, where is the sun? I read this morning, I read something about artificial neural networks by Suzanne Kang on the scan blog. Then you might actually find this fairly familiar because it's exactly the same linear weighting that you have in neural networks. It's just a weighted sum of things. Here you would only have, you could call this like a 2-layer or a 1 weight layer neural network if you want. But you could also not do that. So the point is that each electrode time course results from a weighted sum of these independent components. And then what this figure also shows is, now if you, for example, say this independent component here, C2, this is artifactual, this is something that I don't want in my data, then you could, of course, set all the weights that go from the independent components C2 to your electrodes. So here, W21, W22, and W23, set them to 0. And then you would get what you see here in these dashed lines. Essentially, the dashed lines are a little bit higher here because this negative contribution of of component C2 is not does not enter the mix for each of these electrodes anymore. Yeah, so that's the general idea without formulas of independent components, their weights, and the resulting electrode time courses. The thing is now that, of course, your observed data corresponds to the electrode time courses. And what you have not observed are neither the weights nor the independent components. Yeah? And that's the big difference to something, for example, like the GLM, where you also need to estimate the weights, so the beta parameters, but you have a hypothesis on these latent things. Yeah, so you have a hypothesis on your regressors, which you use in an informed way because you did some manipulation. So if you want, you can also see this as a design matrix that you don't know and that you need to estimate from the data simultaneously with estimating the parameters. It's really quite cool that something like that works. But it also means that you're doing this in a fairly non-informative, in a fairly non-informed way at this level. So, questions about this slide? No? This is then the next slide. That's a great talk. I talked about one slide, now we're talking about the next slide. This is then a slide that tries to show what's happening in ICA without using math, but maybe a little bit of math, which one can do, and sometimes it's actually helpful. It's obviously nicer if you then also do the math. So what this tries to show is that you acquire sculpt data, so you have time points and channels, so these are your electrodes. You see that there might be a little bit of alpha activity going on in the region where I just circled. And then what you do, and this is actually the nomenclature, and so in this sense, actually, this slide is helpful, is that you use ICA to decompose your data into independent component activations and, I would say, weights. These weights you can visualize for each electrode and each component, and then you can project them onto a sculpt map. Let me check. Yeah, in a second I will be able to explain where this is coming from. But these are the weights that we just seen there. So this is the estimation of these weights. And what we see here is the estimation of the IC of the independent components. So the first thing that is really confusing is how many components do you get from a certain recording set. You get as many components, independent components, as you have recording channels. So for example, if you have 64 electrodes, you get 64 independent components, and these components, like in the slide before, have an evolution over time. They are, however, latent in the sense that they were never really observed, but if you multiply them with the weight matrix at each time point, so this little star here is supposed to mean a matrix multiplication. If you multiply them, then you would do, of course, row times column. Then you would get the first pattern here over channels, and then we repeat this for all time points. And why this is always visualized in terms of these topographies is because this weight matrix is channels by components, which is just it's a square matrix. So it's if you have 64 channels, it's a 64 by 64 matrix. And then of course you can, if you do this matrix multiplication, you of course need to go over components and weight your components, but you can of course also look at the channel dimension. And if you look at a column here of this channel dimension, then you have for each channel you have a weight. Yeah? So for each channel you have a number, and then you can of course associate these channel weight or plot this on a topography. I think we will see larger ones. They are a little bit small. So what I mean by these topographies are these things. You can visualize a column of this matrix on the because each value refers to an electrode. You can visualize this in this topography way and then look at it. But it is really just a visualization of the weights that you get from the basic definition of the ICA. So this is the decomposing step of ICA artifact correction. Then what happens is that you actually select independent components, and you decide to throw out certain ones. Usually people are a little bit confused when they actually do an ICA analysis with some software, that they don't get 64 independent components back, but usually if they have 64 electrodes, they only get 10 or so independent components. But this is just due to the fact that the software automatically discards a lot of independent components that don't contribute to explain variance in the data. And then you're only faced with the challenge of actually looking at like 10 independent components or so. But there are 64 independent components. If you have 64 electrodes, there are 64 of these weight maps. Then you can, as I'll show you in a second, decide which one you want to keep, which one you want to take out. And then, just as we saw here, if you set the weight then to 0, then a certain independent component does not contribute to your data anymore. So let me show you first this. this shows the notion of statistical independence of IC activations over time points in the following sense. Here you have independent component 1, and here you have independent component 2. Now, if you look at this plot, these are of course time series, and you can now of course plot their relative relation so you get a two-dimensional thing for each time point. And if you do that, then you don't see a strong correlation between them, but you see that they are independent over time. And this is why, in this sense, in the cognitive neuroscience, psychology, ICA explanation, these things are independent. Actually, what you're trying to do is minimize the Gaussianity of these independent components. But this you will find in my book in autumn, and maybe I teach that in the next summer. Who knows? So that's the notion of independence. Now, why is this interesting in EEG research? Because what people do for eye movement correction is that you identify artifacts. So this is the original EEG, and these are not the corresponding, but the resulting ICA components that you get from estimating the weight matrices and these independent component processes. And then your task is to look at the ICA time courses and their associated topographies and decide, okay, that's artifactual, that's not artifactual. And the way you decide that is based on, I would say, your internal model of the noise. So you, for example, say, okay, here it peaks something, that must be an eye movement thing. And you also have this weight that this is coming primarily from somewhere in the eye. So, well, this might then be a eye movement artifact. So you decide in the back projection of your independent components to not use these anymore. And similar things you can do, for example, for things where you have muscle activity, which is, for example, strongly over temporal electrodes, and then say, okay, this is a muscle artifact. So really what you need to look at, for example, if you have 70 electrodes, that you have 37 ICs, so the independent component traces, which I'm not showing you here on this slide, but they're associated topography. And then you can say, okay, this is a typical eye blink topography, and this, for example, is a typical horizontal eye movement topography. And then you decide to set in your back projection the weights of these components to 0. And then what you get is the following. So this was the original EEG. And then in the IC time course, this variability here gets projected to, in this case, to a single independent component trace, for which you then can set the weights to 0. And if you reconstruct your EEG data, so what is then called your corrected EEG, you see that it's better, maybe not completely perfect. Yeah? And the same thing for saccadic eye movement correction. So variability in the original EEG data over multiple channels is projected to a single IC in this case. And after correction, so setting the weights for this independent component to 0, you do a little bit better. So that's the general IC logic. The reason why I'm personally not overwhelmed by independent component analysis, although I find things interesting about it. So first of all, that you estimate two things at the same time, the weights and the independent components, add that you exactly then manage to project certain variability onto certain components. The thing is, in the end, you have to use your internal model again to decide what is artifactual and what is not artifactual. Or you can further standardize that and then say, okay, I model the data with something like this. This needs to go into the data in a certain way. And then you could also have a standard forward model. And there are these approaches that go about things this way. So The thing is that the only thing that I try to stress about ICA, it's okay, but it's not model free. So the model just comes in at a quite late time point. Seems to be a topic and a theme in cognitive neuroscience. It's the same, like the spatial model for fMRI comes in at the last step, namely in terms of random fields. And here the model comes in when you select your independent components. So that's essentially how EEG artifact correction, especially blink correction, works for EEG with ICA. Questions about this? No questions. Good. Then let's go on. Yeah, so let's also, just because you, of course, are interested in terms of your time allocation, how ICA-based artifact correction works, that's, I think is something that's nicely discussed in an oral exam, because it's not like, what is a high-pass filter? It's a filter that lets high frequencies pass. That's a little bit boring, but ICA-based artifact correction, there's a little bit more to talk about. Good. Then let's go to event-related averaging, which is not that much to talk about. So, of course, event-related averaging works as you would think it works. So you have multiple trials. So here you have the single trial 1, 2, 3, 4, and so on, which are all epoch. And you see that there's considerable variability for the single electrode in terms of the trace. Now, if you start averaging, and this on the right hand shows the average of 1, 2, 3, and increasingly more, so you want cumulative averaging of increasingly more trials, you see that this kind of acts like a low-pass filter. So what you get in the end is less wiggly, and also the overall extension, or the how much the potential deviates from zero actually decreases, which is good to know, because if you have one condition where you average a lot of trials and one condition where you only acquire a few trials, in general you would assume that you have some more deflections in the potential in the condition where you have less trials. But in the end, it's just averaging of each time point, and there's nothing really conceptually interesting about this. Then, of course, and this is something that I showed you in the very beginning, you can have between subject variability, as shown here, where you can have really different things between participants, and these very nice ERPs that you then see in papers usually result from averaging multiple subjects. Actually, here this is a subject. This is actually within subject variability over different sessions, which it's not really clear whether these are runs or sessions. Well, they took off the EEG in between. I would doubt it. But there is variability. This is what this whole thing just means. But I showed you a real life example of that in the very beginning. Then, of course, one problem that you have when you do event-related averaging is that if you have considerable latency variability, then you might run into the problem that on average, in your average, you don't have a good representation of what happens on the single trial. So this is the example here. I think I will actually skip the right one. So the example here is the following. On trial 1, trial 2, trial 3, and trial 4, you have these kind of Gaussian shaped bumps, but they all have kind of a different latency. And then if you compute the average, you will get this thick black line here, which does not really reflect what happened on a single trial. Yeah, so on a single trial, the bumps actually were smaller, but they were variable over time. Same here, with a little bit of a different width of the whole thing. Even more complex here, where you have positive and negative deflections on different trials, which then do overlap in time in such a way that on average you just get you basically don't get anything, so you get zeros because positive and negative deflections in the potential cancel out. And this whole latency variability thing, and especially that you have kind of these things that cancel each other out, this actually motivates the whole time frequency analysis bit. So where you basically avoid canceling out power, as it's then called, that is due to phase shift. So we will see this plot again that when we talk about frequency analysis. And because time frequency analysis is actually to alleviate this problem that you might have things cancelling out. This example. It's a little bit of a complicated experiment that you can read about in the log book. Will not be quizzed in the exam. The important thing about latency variable, and then we will come back to this thing. So that's kind of a serious search experiment. Then something else that is also related to averaging is the notion of steady state ERPs, which has to do with ERPs and averaging, but is actually something quite confusing. And because steady state ERPs, they actually refer to an experimental paradigm. So you would think that steady state ERPs refer somehow how you compute ERPs. No, they actually refer to the way that stimuli presented and that then affect how the ERPs look. So the standard thing that we've discussed so far is that on a single trial you have this kind of transient response, and then if you average things, then you get these C1, P1, and 1 components, for example, in the visual domain. Now this always assumed that there was a single stimulus onset, and then at least for like 250 milliseconds or so, nothing else happened. Yeah? But of course, you can present flickering stimuli that give a new drive to the system already when the response of the visual cortex is not done. And when you then average the responses, this is what is then called steady state ERP. So here you present 6 on 6 Hertz, so you get some overlap. When you average, and if you go to higher and higher frequencies, stimulation frequencies, you essentially see in the ERP the frequency at which you drove the stimulus. So the point here about this slide is actually more to learn about the term steady state ERP than to learn about some specific form of averaging. It's really the paradigm that is different in steady state ERPs to the paradigms that are used for standard ERPs. Good, that's steady state ERP, which one should at least have heard, because especially if you, for example, work with Felix on EEG, they use these kind of steady state ERP stimulation types quite frequently, because they use these tactile, quite long extended vibratory stimuli, and there what you can do is look at the frequency power, look at the steady state ERP, but you don't have a single ERP because you don't have a single stimulus that is distant in time from other stimuli. Then ERPs. Now that you computed the average, you're still prone to plot them, and there are different ways you can plot them. As discussed in the LUC and also in my world, there's kind of the old school plotting that you see in certain publications, which are old, and I think the main reason is that they didn't have the software to do that nicely, where you have the axis, and so the time axis and the voltage axis somehow removed from actually the trace. The trace you find somewhere in the figure, and somewhere else you find the axis. Or one can do that better these days. Here you see an example that is a little bit more recent, but which still has the kind of follows the weird convention that negativity is plotted upwards, and that also you don't have the trace really on the line. And when I started EEG, I thought one should actually follow these conventions because that's EEG. But then at one point I said, no, that doesn't make any sense. And I was happy that also Steve Luck think that doesn't make any sense. So this is the normal way you plot any kind of things: positivity upwards, negativity downwards, and with axis annotations. Just that you need to, if you look into EEG literature, you will see these things, and you should not be confused. It's just the way they plotted things back in the days. And as you read in the Luck book, nobody knows why they did it. And then, from my perspective, once you have plotted that, you're actually done with your ERP analysis. Because what I'm then interested in is to, mainly what I'm interested in is to come up with a biophysical model that now explains this ERP trace, which you might want to extend to single trials. Then you get rid of this whole averaging business, or you might do the whole thing in the frequency domain, that you explain an average frequency response to a condition with a biophysical model, whatever. What a lot of people do, and also of course I do, in a more simplistic manner, is now not trying to explain these kind of traces by neurobiological models, but go on and try to press them a little bit for condition differences. And then you can start your own science on how you want to quantify differences in ERPs and evaluate these differences for statistical significance. And there are cons and pros for all kinds of things. So, for example, if you find, in this case, in condition A and condition B, well, here the two traces, well, they overlap at least on the baseline, but they seem to be different most of the time. You can ask yourself, how reliable is this difference? And then my personal take on this is that you should look into your single participants and then look at their respective P3 responses. And then you already have the problem that the P3 response in certain participants will be earlier and certain later. Sometimes you might not see it at all. And you have to kind of look, okay, is this P3 in these participants? And you should convince yourself that if you see something on the average, that you see this in the majority of your participants. And if you do so, then I think it's worthwhile reporting this as a group effect. You can, of course, also then do some sort of statistic comparison in the sense that you, for example, extract the effect amplitude in a certain time window for one or the other conditions, and then use these amplitudes in a paired sample t-test, for example. But these paired sample t-tests, of course, will only come out significantly if this actually happens in the majority of your participants. So this is why, of course, you can go and do all sorts of tests on this without looking at the participant data and then hoping that it gets significant if you do some more tests. But if you do these tests over participants, then I think the easiest is to just look at them and look how reliable that is. And then if you report that there's a difference between your conditions, if you have that on the average, and maybe that's your main figure in the paper, but in the supplement you include ERP from these two conditions from each participant, and for the majority, let's say 15 of 19 or whatever, and in these days now that we acquire more like 40 participants, in 30 of these 40 participants this is there, then you can say, yeah, I somehow believe that this is there. You can, of course, also go in much more detail about trying to establish an experimental effect by not looking at, for example, local peaks, but looking at average peaks after low-pass filtering, which of course makes sense if you usually what you have on the participant level looks much more like this than this, because if you look at the maximum peak, then of course here, because you have a maximum here and here actually at the edge of the measurement window, you might be a little bit misled. So if you do these quantifications but this again goes into the direction of what I just said. If you're extracting ERP data from each participant according to some rule, for example, you look into a certain measurement window and you're taking the maximum, you should then still check visually and from your feeling of reproducibility over participants whether this actually makes sense, because it doesn't make any sense if you see in 4 participants it looks like there is something and in 36 it doesn't, but your t-value is significant, then it's like, well, then somehow your t-value doesn't measure what you wanted to measure. Then you might have gotten into edge effects. So personally, because you can start long discussions about what's the measurement window. Should it be a little bit more here? Should it be a little bit more there? Should I, instead of looking at peaks, should I look at the area? It might make a lot of sense to look at the area, but then you still might have reasons to just look at the peak for things of kind of different shifts between the baseline for participants and so on. So at this level of ERP research, maybe I'm communicating this also a little bit here, is where I find it like, yeah, let's not make a science of these things. Let's rather make a science that relates more to the neurobiology and come up with interesting neurobiological models that explain this, where you, of course, then try to explain not a single peak or a single area, but you try to explain the whole potential time course over the entire electrode set based on neurobiological principles. So I think it's better to, from my perspective, to invest time there rather than to in these kind of discussions how to do it there and there. And you will also find that there is no single best way to do these kind of things. So you will also be hard prone to find any recommendations. Sometimes you find them and then it makes sense to follow them. In the end, it's also a question of how the person that you work with, so maybe your supervisor, how they have always done it, and then you will also do it like that if you do an EEG experiment. Good. So we are a little bit early, but then we discussed a little bit more in the beginning. So we talked today about concepts of artifact correction, specifically ICA-based artifact correction, event-related averaging. That, from my perspective, there's not so much to talk about, and ERP quantification. Yeah, do it if you want to establish condition-specific effects. There is, of course, also by now the whole random field theory analysis for MEG and EG data implemented in SPM. So this is also a way to quantify in terms of the statistical significance effects over electrodes in time windows, which is somewhat nice because it doesn't focus. So in these kind of things, that's another thing. Here you always look at a certain electrode or a subset of electrodes, but really you want to do this over the whole space of electrodes. And these random field methods, they actually allow you to account for the whole space over which you do the statistical comparisons. So yeah, that's another way to do ERP quantification. Yeah. But what I then want to follow this up with in the next last sessions is actually how to make sense if you have an ERP of where it's coming from. So that would be source space analysis, or not to do ERPs at all, but do frequency analysis because of this latency variability issue. Questions at this point? So the important points from this section are really the concepts of artifact correction and the ICA-based artifact correction and steady-state potentials. Yeah, no questions? That's good.
So you said there was some problem with the ICA-based approach because you have to estimate the rates and
the independent ones.
And there were also problems with the concepts that we discussed before, the fixed threshold. So the alternative would be we didn't really discuss the bit where you have to.
No, I mean there are. I mean, with ICA, the ICA on the technical level that works. So it estimates the weights in the independent components, so you get estimates for them. What is then the tricky thing is to decide which components to include and which not, which is straightforward for some components, but not so straightforward for other components. So there is where you actually then have to follow your heart or whatever. So, or in another way where the objectivity gets a little bit lost because you have to decide how to do that. You can again try to follow some community guidelines, but then you're basically following the peer pressure guidelines, which also makes sense. I'm not saying you shouldn't do that. Of course you should do it. But there's again it's not the perfect method that is completely objective and is right. And as the same thing applies to these artifact thresholds. So one way one can do things, of course, is to be on the safe side, is to do some ICA-based artifact correction to get rid of idlings. And then after one has done that, still use a threshold to, for example, if one thinks one missed a little bit, to use an absolute threshold so that one is sure that in the all the epochs there's never a value that extends a certain value. We'll also usually see that sometimes you have really artifactual epochs, and then if you compute the grand average, your grand averages will look weird, and as soon as you just exclude a number of trials that follow these kind of threshold detection, you will get ERPs that look much more like the ERPs that your colleagues and the whole EEG community has recorded. So yeah, there is constant debate of how one should do certain things. I think we looked at did we look at the high pass and low pass filtering last week? I was under the impression that I showed them recently. Or did I take them out of this lecture? Let me have a look. Because I recently saw these plots again. No, because this is actually what I think is the most important thing about the whole pre-processing business. No, they come. No, I know. They come later because they are in this frequency issue thing. Let me show you this because it relates to what you just asked. So there we go. So we will come back to this because we will talk about filters. But filters, so essentially all these artifact correction things are, you can view them as filters. So you're interested in interesting stuff and you want to get rid of non-interesting stuff. And what I think is important is actually what is shown here, that you do these things yourself. So this actually shows the data that is in these folders. So the Smith et al. Data, and Sophie Planck, she analyzed parts of this data quite well for her project report back in her days, 2014. And this is showing data for the high and the low contrast, and it shows. Let's zoom a little bit in. It shows let's do that here. High contrast, low contrast, and this is the better electrode. Okay, so it shows the effects of a specific filter offset, which is this case the low pass filter. So this is a low pass filter, but you can you should interpolate that this can also be the effect of artifact correction. And then what I think is important is that if you're interested in the differences between two conditions, in this case high coherence and low coherence, so this trace, sorry, no, it doesn't work. So the black trace and the black dash trace, and you look at this as a function of the filter settings or as the function of your algorithm, then you might find that this affects the data really a lot, like it does actually here. So if you use a high pass filter with a cutoff of 10 Hertz, which is really low, nobody does that, so the usual cutoff is 40 Hertz, then you actually affect the trace that you get quite a lot. What you don't affect, which is also good to know, is the difference. So for the high contrast versus the low contrast, sorry, because you cannot see this. This is the high contrast and the low contrast for the 10 Hertz, and this is the black one, is the high contrast and the low contrast for the 40 Hertz low pass filter. Could be ICA-based averaging, ICA-based artifact removal or threshold things. And it's important to look at these things to get a feeling how much they affect, and then the whole thing. And then if you find that your condition-specific effect, which explains consciousness, is completely absent if you change the filter settings a little bit, then maybe you believe in your consciousness effect should drop a little bit, which is unfortunate, but that doesn't matter because you are also able to publish null findings these days, and everybody who tells you different should better leave science or whatever. So then you could have a nice paper that says there is no consciousness effect on this. So to get other people then hoping that they find consciousness effects. But it's important to look at these things, because if they are kind of robust over different pre-processing settings, then you might believe them more. So no wrong or right artifact correction, but informed data analysis. It's good for your personal feeling and for science in general. Good. Anything else? No? Good. Then see you next week on Monday.